Hello, welcome. Hope you're all doing well. Today we're going to continue our sort of introduction into quantum mechanics. And so if you remember at the end of last time, we're talking about how at the end of the 1800s, physics was kind of static. They kind of thought they'd understood quite a bit, right? We had Newton's laws of motion that described particles and the way objects move in space, right? And we had Maxwell's equations that described light, right? And those two were very, very different. But then that started to unravel, right? And the first thing we saw last time was black body radiation and the failure of the Rayleigh-Jeans law to explain the spectrum of black body radiation. And in 1900, Max Planck solved that by introducing the quantization of energy in these oscillators, right? And so that was kind of the first step. The second step was the photoelectric effect. So the photoelectric effect is what happens when light strikes a metal surface, some metal surfaces, and the energy from the light causes the emission of electrons, all right? And these electrons carry away with them some kinetic energy, right? And remember, the kinetic energy that they carry away is equal to 1/2 mv squared, okay? So you can set up a little system like this where you have an evacuated chamber, you have light coming in, it causes electrons to be emitted, and those electrons, that electron current can then be measured, right? In a little setup like this. So a couple of things. First of all, the light energy has to be greater than the binding energy. In other words, the electron will be emitted, the electron will be kicked off the surface if the light energy is enough that it overcomes the energy with which the electron is held to the metal, all right? And that's sometimes called the binding energy. So for this photoelectric effect, what people expected was, well, okay, if you just provide enough light energy, you'll eventually emit an electron, right? And so even if you had a dim light, if you just waited long enough, you would see an electron emitted. So for a dim light, they expected what they called a lag time, right? It took a while for enough energy to build up to kick off the electron. When they actually looked at this and did the experiment, what they discovered was something quite a bit different. So first of all, with the dim light, there was no lag time. There was no lag time for dim light. Instead, what they saw was a very severe frequency dependence or wavelength dependence for the photoelectric effect. At low frequencies of light, over here, right, there was no emission of electrons. And then no matter how intense you made it, you couldn't get any emission of electrons. And then as you increase the frequency or shorten the wavelength, you get to what's called a threshold frequency. And this was a surprise, right? Why was there this threshold frequency where all of a sudden, boom, you got the emission of electrons? And then the intensity of the light, all that did was increase the number of photoelectrons that were observed, right? So here's lower light intensity, fewer photoelectrons. Higher light intensity, more photoelectrons. But below the threshold frequency, it didn't matter how intense the light was, there were no photoelectrons emitted, right? So how could we explain this? Well, in 1905, Einstein suggested a remarkable idea, and that is that light is quantized. Light is composed of particles. We saw in black body radiation that Planck solved the problem by assuming that the energy in these oscillators were quantized. Now Einstein was suggesting that light was quantized. So in the sort of wave picture of light, if you think about a flashlight, it's emitting these waves of electromagnetic radiation, right? If light is a particle, then a flashlight is emitting a bunch of light particles, which are called photons, right? Photons of light. Einstein's equation that explained quantization was E is equal to h nu. This is the energy of a single photon. Right? And if we plug in the equation nu is equal to c over lambda, we get E is equal to h c over lambda, right? And so these two equations describe the quantization of light. So how did this explain the photoelectric effect? Well, the idea was that in order for there to be a photoelectron emitted, right, a single photon of light had to have enough energy to overcome the binding energy, of the electron in the metal, right? So a single photon had to have enough energy. So you couldn't have multiple photons coming in. It had to come from a single photon. And so you can see that the energy of a single photon, right, is equal to h nu. So at some frequency that was too low, the photon wouldn't have enough energy to dislodge an electron, right? And that's what was happening in this region, right? A single photon didn't have enough energy to overcome the binding energy of the electron. The threshold frequency is where the photon then had enough binding energy to overcome, enough energy to overcome the binding energy. And then, of course, lower versus higher intensity light had more photons, right? So it caused the emission of more photoelectrons, yeah? So an analogy here, we can sort of think about it this way. At low frequencies, or long wavelengths, each photon doesn't have enough energy, let's say, to dislodge an electron. That'd be kind of like saying, okay, if we have a window and we're throwing ping pong balls at it, it doesn't matter how many ping pong balls we throw because no one ping pong ball has enough energy to break the window, right? So those low energy photons just don't have enough energy to kick off an electron. On the other hand, if we throw a baseball at the window, that does have enough energy. So that would be like my shorter wavelength, higher frequency photon, right? You got to have enough energy in one photon to overcome the binding energy, right? And so that is the idea then behind light being quantized, right? So notice that based on this, we can have a question like this: which wavelength of light has higher energy per photon? Red or blue? Well, blue light has shorter wavelength, right? And higher frequency, therefore it has higher energy. So remember last time when we looked at this spectrum, I said that the photons over here, now we know the photons over here have much lower energy and the photons over here have much higher energy, right? And it's right visible in the middle where a single photon has enough energy to begin to interact with chemical bonds, right? And that's why in this region we can begin to see, right? Ultraviolet region, the single photon has enough energy to break chemical bonds, which is why it causes sunburns and stuff like that. And then X-rays and gamma rays have even more energy than that. All right, so the photoelectric effect, the equation that then we can govern, that we can use to understand it, is that the kinetic energy of the emitted electron is equal to the energy of the photon, h nu, minus the binding energy of the electron to the metal, all right? So if we know the kinetic energy is equal to 1/2 mv squared, right? And so we can say that for the photoelectric effect, we can calculate the velocity of the emitted electron. 1/2 mv squared is equal to h nu minus phi, the binding energy of the electron in the metal. All right. So this is the mass of the electron, right? This is the velocity that it has when it's emitted. All right. H nu is the energy of the photon. And phi is the binding energy of the electron. The binding energy is the amount of energy with which the electron is held to the metal, right? So notice that until the threshold frequency is when this energy is high enough, right? So that this minus this is positive, right? That's where the threshold frequency occurs, yeah? And notice that if the electron has more energy than the binding energy, what happens to that extra energy? Well, it just becomes kinetic energy, right? And so the electron will have a higher and higher velocity as the frequency gets higher and higher, right? Past the threshold frequency. All right, let's just do a couple of quick examples here. The first one would be, what is the frequency of radiation that is required to supply 1 times 10 to the 2 joules of energy from 8.5 times 10 to the 27 photons, right? So we're given that we have 8.5 times 10 to the 27 photons, and we're given that we have 1.0 times 10 to the 2 joules of energy, right? And we're trying to find the frequency, right? So that we know for a single electron, right, we know that the energy of that single photon, for a single photon, the energy is equal to h nu, right? But this is saying how much energy do we, what frequency do we need if we have this many photons with this much energy? Well, then we have to figure out, okay, how much energy per photon? So the energy of a single photon that would provide this amount of energy is going to be equal to the total energy divided by the number of photons, right? And that's going to be equal to 1.0 times 10 to the 2 joules divided by 8.5 times 10 to the 27 photons, right? And that comes out to be equal to 1.176 times 10 to the minus 26 joules, right? And that's the energy of a single photon, okay? So if we want the frequency of that photon, then we just use this equation, right? And we say nu is equal to E over H, right? So that's equal to the energy, 1.176 times 10 to the minus 26 joules, divided by H, 6.626 times 10 to the minus 34 joule seconds, right? The joules cancel out, and I'm left with 1.8 times 10 to the minus 7 per second, which is equal to 1.8 times 10 to the, let's see, I don't think that's right. Hold on. I apologize for that. I just accidentally put a negative sign there. It should be +7, okay? So it should be 1.8 times 10 to the 7 per second, which is 1.8 times 10 to the 7 hertz. Okay, here's a question for you. We're not doing learning catalytics today, so this is just an asynchronous lecture, but it'd still be helpful for you to think about this. So I'm going to read the question and then go ahead and pause the recording if you'd like, and then you can think about it, and then I'll reveal the answer. So the question is this: if you shine light of 3 different wavelengths, 325 nanometers, 455 nanometers, and 632 nanometers on a metal surface, the observations for each wavelength labeled A, B, and C are: observation A is that no photoelectrons are observed. Observation B is that photoelectrons are observed with a kinetic energy of 155 kilojoules per mole. Observation C is that photoelectrons with a kinetic energy of 51 kilojoules per mole are observed. So what I want you to do is figure out which observation corresponds to which wavelength of light. You may pause the video now and figure this out, and then start it as soon as you're done. Okay, the correct answer is that observation A is the 632 nanometer light, right? It is the longest wavelength and therefore the lowest energy. So if any of the three wavelengths were going to produce no photoelectrons, it would be that one, right? Because it has the lowest energy. Observation B is 325 nanometer light. Notice that observation B was the one with the highest energy photoelectrons. So it had to be the wavelength that was the shortest, which means that the photon energy was the highest, right? And it gave that extra kinetic energy to the electrons, yeah? And then finally, observation C was 455 nanometer light, and that's kind of in between, right? The electrons were, there was enough energy in the photon to emit photoelectrons, right? But they weren't quite as energetic as the ones emitted by the the smaller wavelength of light. Okay? All right, let's keep going here. So another observation that physicists started seeing was the atomic, the spectra that was given off by atoms, all right? And so let's talk a little bit about the atomic spectra and the Bohr model. So atomic spectra result when you have an evacuated tube with some element in it, usually in the gaseous form, and you pass current through that and they emit light, all right? And what was discovered was that that light was not continuous like a normal electromagnetic spectrum, but rather was in certain at certain wavelengths only. All right. So here's the idea. If you have a lamp that contains an element like hydrogen, for example, take the light, you pass it through a slit, and then you pass it through a prism. And what you find is that you don't get a continuous spectrum of light. Instead, you get light only at specific wavelengths, right? And those are these lines that you see here, right? And this is called emission spectroscopy of these elements, right? And again, how do you explain this? Scientists at the time, people were wondering, well, why isn't this a continuous spectrum? Here's some spectra from other elements. Here's helium. If you had helium in that tube, you'd see something like this. Again, specific lines at specific wavelengths, right? If you had barium, you'd see something like this. And contrast this with the white light spectrum, which contains all wavelengths, right? So how could this be explained? Well, Niels Bohr came up with a simple model called the Bohr model. And in the Bohr model, what he suggested was that the energy states of electrons and atoms were, again, quantized, right? They couldn't have just any old energy. They had certain energies and only those energies. That also meant that they could only have certain radii, right? So in other words, an electron, let's say in the hydrogen atom, could be found here, or here, or here, right? In these orbits that went around the nucleus, okay? But they would never be found in between, right? They would never be found at a radius between this radius and that radius. He introduced the idea of the quantization of energy for electrons, and the energy N of any one of the states was equal to negative 2.18 times 10 to the minus 18 joules times 1 over n squared. All right, n was called a quantum number, and n could be equal to 1, 2, 3 integer numbers going on up. All right, so what he proposed then was that these lines were a result of the electron being excited from some lower energy state to some higher energy state, and then relaxing back down. And the reasons that there were specific lines was because the electron had to go, let's say in this example, from n equal 3 to n equal 2. And the energy difference between those two states then would correspond to the energy of the emitted photon, right? So since these energy differences are all distinct, right, the lines are distinct and they're at certain wavelengths and only at those wavelengths. Okay. These are kind of what the energy states look like if you just plotted energy. So here's the lowest energy state at n equal 1, n equal 2, n equal 3, and so on. And this model did a very good job at explaining the emission spectrum of hydrogen, right? So for hydrogen, which is this one right here, this model predicted that very, very well. Turns out it couldn't predict it for other elements because this model, it was not really a fully quantum mechanical model yet, but it was one step in that direction. All right, good. What I'd like to do now is a little bit of a transition. So I've sort of led you a little bit through some of the historical findings that started to sort of bring up this idea that things were quantized, that energy was quantized at the fundamental level. And it started to break down this barrier between particles behaving one way and light behaving another. Rather, they both behave in a similar way, right, in this quantum mechanical way. So what we'd like to do next is talk about the double slit experiment. And the double slit experiment will help us to understand how these wave particles, if you want to call them that, behave. Now, we got to remember is that things behave very differently on this absolutely small scale, right? We have no direct experience with these particles. The mass of an electron is so small. Its size is so small. There aren't really any particles that are smaller than that. Remember, the electron was initially thought of as a particle. Later, it was discovered that it had these wave-like properties. Light was initially thought of as a wave, and later it was discovered that it had particle-like properties. Luckily, they both basically behave very, very similarly as these wave particles. This experiment, the double slit experiment, shows us how these particles behave, and it's absolutely impossible to explain with classical mechanics. If you can understand the heart of this experiment, you can sort of understand the heart of quantum mechanics. And I want to try to explain it to you without any math, just conceptual, right? So we can get the conceptual idea for what's going on here in the quantum world. So we're going to start, with the double slit experiment with billiard balls, all right? So what I want you to imagine is a billiard table. Right? And the billiard table has a divider in the middle. And the divider has two slits, which I'm going to label 1 and 2. Okay, it has two openings. And I want you to imagine a billiard balls being fired at that divider. All right? And over here somewhere, we're going to have a billiard ball detector, which is going to detect the billiard balls as they come through. All right. What do we see at this billiard ball detector? First of all, first thing we see is that the billiard balls arrive as whole identical particles. Right? We never see any half particles or quarter particles. We don't see any billiard balls that are broken up. Either a billiard ball hits the detector and it registers, or it does not hit the detector and does not register, right? So in a sense, we say that billiard balls are quantized. They come in packets of 1, right? Their intensity is not continuously variable, right? It's 1, 2, 3, 4. You can't have 1.157 billiard balls, yeah? Okay. So that's the first thing we notice. The second thing we notice is if we open hole 1, we get a probability plot that looks like this, P1. So I'm going to draw the probability plot over here in red. And this is going to be P1, right? In other words, and I'm just translated that from over here, right? So there's the greatest probability of the balls hitting here as they come through, right? But depending on the angle and everything, they could hit a little bit out here, a little bit out here, right? And you get this probability plot that looks kind of like that, okay? If you open hole 2, you get P2, right? And P2 looks kind of like P1, but it's just shifted over so that it's behind hole 2, right? And then if you open both holes, if you open 1 and 2, right, you get simply the sum of P1 and P2, which didn't draw this very well, but maybe it looks something like that. Okay, these should overlap a little more. So they add together here, and you get the sum of those two. All right, so you open hole 1 and 2, and you get P1 plus P2. All right, does that make sense? All right, what happens if we repeat the same experiment, but now instead of billiard balls, we do it with waves? All right, so just think of a shallow tray now instead of a pool table. All right, we're going to imagine a shallow tray, and that shallow tray is going to have water in it. So double slit with waves, double slit experiment with waves. So it's going to have a little wave maker here, just something that goes up and down, right, and produces waves. And the waves are going to emanate out, and then they're going to hit a barrier that has 2 slits in it, right, 1 and 2, okay. And then the waves are going to come out of those, right. And we learned last time about diffraction, right? Diffraction and interference with waves, okay? So again, over here, we're going to have a wave detector, and the detector is going to detect the intensity of the wave wherever it hits along that surface, all right? So what do we see in this case? First of all, we see that the waves arrive with a continuously variable intensity. Right? What do I mean by this? I mean, waves are very different than billiard balls, right? The billiard balls come in packages of 1, right? So we have 1, 2, 3. But the wave height, right, that hits here is continuously variable. It can be, let's say, I don't know how big these waves are, but let's say it's like 5 inches, 4 inches, 3 inches, but it could be 3.127 inches. It could be anything in between, right? The wave height is continuously variable. It can be anything from very, very small, from 0, right, up to some bigger number, and everything in between, all right? That's what I mean by continuously variable, yeah? Secondly, if I open hole 1, right, I get P1. P1 looks a lot like what we saw with the particles, billiard balls, P1, right? The greatest intensity is basically right here, right? And if we open hole 2 and close hole 1, we get P2, and P2 looks just like P1. It's just scooted over a little bit, right? P2. But now we get something very different if we open both of them, right? So remember last time when we opened holes 1 and 2 with the billiard balls, we just got a addition of P1 and P2, right? Let's see. We go back to here, right? Remember when we opened both of them, we got P1 plus P2. Now, if we open both of them, we get an interference pattern, characteristic of waves, right? So if I do that, it's going to look something like this. It's going to be greatest here, and then it's going to oscillate and go down. Right, something like that. And so remember we talked about this last time, right? Waves have this characteristic of diffraction and interference, right? So if the wave travels through here, this leg is the same distance as that leg, and you get constructive interference, and that's where you get a peak, right? If you move over a little bit, right, this leg is longer than this leg by exactly half a wavelength, and you get destructive interference. And if you move over a little more, the two lengths differ by an entire wavelength, and you get a constructive interference again, right? And so you see this interference pattern from the double slit experiment with two waves. Notice you can kind of see that here, right? Here's where it's constructively interfering, destructively interfering, constructively interfering, and so on, okay? So that's the double slit experiment with waves. Now, we'll move on, and we want to do the double slit experiment with electrons, right? So what happens when we do this experiment with electrons? So now we're going to have a source of electrons. Could be a filament, right? And that's going to just boil off electrons, and the electrons are going to be accelerated through some sort of electric field. I won't bother drawing that here, but the electrons are being given off, and they're going to hit a barrier. And the barrier is going to have two slits in it, right? Which are 1 and 2, right? And then over here, we're going to put an array of electron detectors. Right, a whole bunch of little electron detectors. All right, and these electron detectors can detect electrons. Whenever an electron hits it, you hear a click. Right, click, 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 click when an electron hits, and it registers the position of the electron as to where it hits. So you can put that out onto a computer, right? You can get a graph. You know, let's say going from detector 1 to detector 1,000. Let's say you have 1,000 of them, 1,000, right? When an electron hits, you get a little increase in that particular detector, whichever number it was, okay? So what do you see here with electrons? So first of all, the first observation is that you either hear a click or you don't hear a click. In other words, you turn this filament on, electrons start coming through, and you hear these detectors start clicking, right? And you see the electrons here on your graph. You see where they land here on your graph, yeah? So what you see is that some detectors are clicking more than others. Why? Because there's more electrons hitting them. Some are not clicking very much at all. Why? Because there's no electrons hitting them. But what you never hear is a half click or a quarter click or a tenth of a click, right? You either hear a click or you don't, right? What does that remind you of that we've seen already? Billiard balls, right? You either get a billiard ball or you don't. You either get an electron or you don't at this array of detectors. So the electrons arrive as, so what do we say for the billiard balls arrive as whole identical particles, and we're going to say the same thing for the electrons, right? Electrons arrive as whole identical particles, okay? I'm just going to put in here no half clicks, right? No quarter clicks, right? Nothing like that. So far the electrons are kind of behaving like particles, yeah? Waves, on the other hand, right, would have a continuously variable intensity, right? So you'd hear a continuously variable size of click, right? But that's not the case here. They're arriving as particles. Okay, the second thing you notice is if you open hole 1, you get P1, much like we might expect, right? So if you open hole 1, you get P1. If you open hole 2, you get P2, right? Open hole 2, you get P2, right? But, and here's the strange thing, if you open both of them, you get an interference pattern, right? And that would all be read out on this graph, right? That where each of these detectors are coming in and telling you how many electrons are hitting, right? So you can read it on this graph, but it would look very much like we saw before with light, right? Okay. So you get this interference pattern. Okay, so what's going on? How are these particles? Let me show you the next slide here. So this is kind of what we expect here for particles like electrons, right? You have a particle beam, go through 2 slits, and they produce a bright spot here where most of the electrons are landing in here, right? That's like P1 and P2, right? But instead, what we get is this, right? We get an interference pattern. Notice here, there's sort of a dark spot here in the middle, right? Whereas here, there's a bright spot in the middle, right? So this is kind of what we expected for particles, but this is kind of what we got, right? We got this interference pattern. So how do we explain that? Well, maybe it's the case that the electrons have some sort of wave property, right? And maybe the electron kind of goes, okay, one electron goes through here and one goes through there, right? And they meet at the detector. And if they travel the same path, they constructively interfere. But maybe if the 2 electrons travel different paths, then they destructively interfere, right? We can maybe have a hypothesis like that, right? Either it goes through one hole or the other, and 2 electrons coming together because of their properties form this interference pattern. That sounds like a reasonable hypothesis, right? Well, turns out there's a way we can kind of test that hypothesis. What we can do is we can set up a laser. So if we have our, well, let me just go back to this drawing. We can set up a laser right here. All right, so we can set up a laser here. Now, what the laser would do is it would tell us what hole the electron is going through. Okay, why is that? Because when an electron beam passes through a laser beam, it scatters some light, right? So when an electron goes through here, it would scatter a photon, right? And that light can be detected. In other words, what we'll say for our purposes is that when an electron crosses this beam, it creates a flash, right? So if it was going through this slit, it would create a flash coming from here. If it was going from this slit, it would create a flash coming from there, right? And so we can monitor sort of which hole the electron was going through. And if our hypothesis, that is our hypothesis that the 2 electrons go through at a time and they interfere with each other, then we should be able to see these electrons going through by seeing flashes from this laser, right? But we want to do something. We want to do something even more telling than that. In order to eliminate the possibility that there are 2 electrons going through at a time, let's turn this filament way, way down. All right? Let's turn it way, way down so that there's only one electron produced per hour. All right, we're going to turn it way, way down so that, in other words, we're going to start to turn this filament down until we only hear 1 click every hour from this array of detectors, right? And what we're trying to do is we're trying to make it so that we're sure there's only 1 electron going through the apparatus at a time. Yeah? Because if there's only 1 going through at a time, then we shouldn't see an interference pattern, right? So we try that experiment, and without the laser first, okay, we turn the laser off, and we try that experiment, 1 electron per hour, right? And we're going to ask, okay, what is the result? What do we see? So every hour we hear a click. We keep track of where those clicks come from, right? For, let's say, several days, right? Until we see some pattern. And believe it or not, we still get the interference pattern, right? We still get the interference pattern, even when we only have 1 electron going through the device per hour. So what we do next, we say, okay, let's turn on the laser and see which hole that electron's going through and how it's still producing this interference pattern, even though there's only 1 per hour. So we turn the laser on, and again, we start hearing clicks. We're going to keep it at 1 click per hour, right? So we make sure there's only 1 electron going through. Sure enough, we turn on the laser, and every time that an electron goes through and we hear a click, we also see a flash, all right? But the flash is either from hole 1 or from hole 2, right? And never from both at once, okay? It's either from hole 1 or from hole 2 and never from both at once. However, with the laser on, the pattern, the interference pattern, goes away. And instead, we just see P1 plus P2, okay? So let me just summarize that for you. So only if we have 1 electron produced per hour with no laser, we get an interference pattern. But if we have 1 electron per hour with laser, right? No interference pattern. Right? So somehow when we turn that laser on, it's changing things. So that instead of getting what we had here, right? We just get 2 bright spots, 1 here and 1 here. And we see a flash either from hole 1 or from hole 2, but never from both at once. Flash from slit 1 or 2, but never both at once. So in other words, when we turn on the laser, the electron is behaving like what? It's behaving like a particle, right? It's behaving just like a particle. When we turn off the laser, even if there's only 1 electron in the device at a time, that electron is behaving like a wave, right? It's behaving like a wave. Okay, very good. So notice though that the electron is behaving differently depending on whether or not we're detecting it with the laser, right? And that's kind of important to quantum mechanics. Remember I said that observation plays a role in the outcome, right? And so when we observe the electron with the laser, it's playing a role in the outcome. All right, well, maybe electrons are delicate things and the laser is disturbing them. What if we try some other things? Like, for example, maybe we use, maybe we turn down the intensity of the laser. Right? Turn down the intensity of the laser so it's not quite so bright. Initially, when we start turning down the intensity, there's no change, right? Every time we hear a click, we see a flash. The flash comes from 1 or 2, never from both at once, and we don't get an interference pattern. All right, we get just P1 and P2. As we continue to turn down the laser, we eventually get to an intensity where you hear a click, but you don't see a flash, right? What happened? What happened was that some electrons got through without being detected, right? Without being seen by the laser, because the laser intensity was too low to catch them all, right? So here's something kind of interesting. If you keep track of those electrons, the ones that weren't seen by the laser, guess what? you get the interference pattern. If you keep track of the two sets of electrons separately, let's say that you find a laser intensity where half the electrons are detected by the laser and half are not, right? All the ones that are not detected by the laser, if you just keep track of those produce the interference pattern. But those that are detected by the laser don't produce the interference pattern. They just produce P1 plus P2, right? Well, how about something else? How about if we change the laser wavelength? What happens if we do that? We make the wavelength, let's say, longer and longer, right? So at first, again, no difference. You hear a click, you see a flash, no interference pattern, right, with the laser on. You make the wavelength longer and longer. Eventually you get to a wavelength that's long enough that you start to see the interference pattern again over here. And you go, aha, now I got them. The problem is that it's exactly at that wavelength where the wavelength of the light is too long to distinguish spatially between the two slits. And all you see is a fuzzy flash from the middle for each time an electron goes through, right? So it turns out there is no way to both detect which hole the electron goes through and see the interference pattern, no matter what you do. Dirac put it this way. He said, there are limits to the fineness of our powers of observation and the smallness of the accompanying disturbance, a limit which is inherent in the nature of things and can never be surpassed by improved technique or increased skill on the part of the observer, right? You can't simultaneously see the interference pattern and detect the slit the electron is going through. All right, you can't do that. So why is that? Well, I'll go through these conclusions here in a minute. But basically, you've come up against the wave-particle duality of matter. Right? We've come right up against the wave-particle duality of matter. The wave nature of matter of the electrons is what produces the interference pattern. Right? A wave can go through both slits and interfere with itself, right? So when we're not detecting the electron, it's essentially doing that. It's going through both slits and interfering with itself to produce the interference pattern. That's the wave nature of the electron. The particle nature of the electron is what allows it to go through a single slit, right? Because if it's a particle, it can go through a single slit, right? And it turns out that these two natures are what we call complementary, right? Complementary. And what that means is complementary, let's describe it as complementary properties are properties that exclude one another. Okay, complementary properties are properties that exclude one another. And that would correspond to the wave and particle nature of the electron. These are complementary. When we're seeing the wave nature, we're seeing the interference pattern. When we're detecting which hole it goes through, we're seeing the particle nature, right? But we can't see both at the same time, no matter what experiment we try to do, right? These two natures exclude one another. Well, it turns out, for reasons that I can't really show you right now, and we'll see if we can get to them a little bit later, but the wave nature of the electron is associated with its momentum, and the particle nature is associated with its position. all right? So the wave nature of the electron and the particle nature are complementary, and so are momentum and position, right? So are momentum and position. So if you can't know, now remember from what we talked about last time in classical physics, right? If you know the momentum and position of a particle, what can you predict? Its future trajectory, yeah? But for electrons, and here's the heart of quantum mechanics, for electrons, you can't know these two things simultaneously, right? That's called Heisenberg's uncertainty principle, and we'll get to that in more detail in just a minute. But you can't simultaneously know the momentum and the position. So if you can't know the momentum and the position, then you cannot predict a trajectory, right? No trajectory, okay? And so in quantum mechanics, what happens is that instead of a trajectory, we get these probability maps, okay? All right, let's draw a few conclusions and summarize all this. So first of all, the superposition principle. The superposition principle is the idea that quantum mechanical particles can simultaneously be in two different states, right? So I'm going to say unobserved quantum mechanical system can simultaneously be in two or more different states. Remember we talked about this a little bit last time with Schrodinger's cat. So for the double slit experiment, right, the electron can simultaneously go through hole 1 and hole 2, right? A single electron can simultaneously go through both holes. We say that it's in this superposition of two states, the state of going through hole 1 and the state of going through hole 2, all right? That's a superposition principle. The second principle is the uncertainty principle, all right? And the uncertainty principle was brought up by Heisenberg, and I'll give you the equation for the uncertainty principle here. This paper. Uncertainty principle says that the uncertainty in the position times the uncertainty in the momentum is greater than or equal to h over 4 pi. X is position, P is momentum, H is Planck's constant, which we've seen before, 6.626 times 10 to the minus 34 joules seconds, right? And notice, this does not apply to baseballs, right? We already said a baseball has a trajectory. Why? Because if we know its position and momentum, right, its future path is determined, yeah? For electrons, this product cannot be zero, which means that you can't simultaneously know the position and the momentum. Why? The position is associated with the particle nature, the momentum is associated with the wave nature, and you can't see both at the same time. By the way, this sort of saved us from a contradiction, right? Because it would really be a contradiction to say, oh, the electron is a wave and a particle. It's not true. More accurately would be to say the electron is either a wave or a particle. Now, it turns out it could be a mixture of both, all right? But it's never 100% a particle and 100% a wave at the same time, okay? And you can see then that these are complementary properties, okay? The other thing we see, so let's just contrast that to the classical concept of a trajectory, right? So if you have a baseball, right, boom, it gets hit in the outfield. It has a position. It has a momentum, right? And based on these two things, right, you can predict where it's going to land, right? If we were batting an electron, right, we couldn't predict where it was going to land, right? Because we can't simultaneously know both its position and momentum. So this is a classical trajectory, right? What do we do in quantum mechanics then? Well, we can't predict that, but what we can predict is probability, right? These classical trajectories are replaced with what we might call a probability distribution map that shows the probability of an electron being in a certain place, right? For any individual electron, we can't predict where it's going to go, but for many, many of them, we can predict these probability maps, all right? So these classical trajectories are going to be replaced in quantum mechanics with probability distribution maps. Similarly, going back to a classical mechanics, right, at baseball, if a pitcher throws a ball, the batter can know where it's going to be and hit it, right? And if it was a quantum mechanical particle, all you would know is probabilities. You'd know that there's a 20% chance of the electron hitting here, 40% chance hitting within here, right? A 70% chance of it hitting within here, okay? And so these probabilities are what replace the trajectory. Okay. Wave nature of particles. So particles like electrons have this wave nature, right? We can see them diffract and we can see them interfere, right? They have a wavelength that's associated with their velocity, okay? So they have a wavelength. It's called the de Broglie wavelength. And the equation is this: lambda is equal to h over mv. All right, where this is the wavelength of the particle, right? Again, h is the same thing, Planck's constant. This is the mass of the particle, and that's the velocity of the particle. Notice that as the mass times the velocity, or mass, and remember that mass times the velocity is equal to momentum, right? So we could write this as, we could also write this as lambda is equal to h over momentum, right? As the momentum gets bigger, right, the wavelength gets smaller, okay? As the particle becomes more energetic, its wavelength gets shorter and shorter, right? Just like we saw for photons, right? As the photon gets more energetic, the wavelength of the photon gets smaller and smaller, okay? Let's do a quick example of this. Let's determine the wavelength of a neutron traveling at 100 meters per second. All right, so we're given the velocity and we're given the mass, and the mass we can look up, the mass of a neutron. And we just want to find the wavelength, right? So we're going to use the de Broglie equation, right? Which is that lambda is equal to h over mv. In order to get the units right, we need to convert the mass into kilograms. So that's the conversion of kilograms. So we convert the mass of the neutron into kilograms, and we get 1.675 times 10 to the minus 27 kilograms. Grams cancel. And then we plug it into this equation. Lambda is equal to h over mv, right? We put in h, put in the mass and the velocity, right? Notice what happens. Meters and meters squared give you meters in the numerator, right? Kilograms cancel and seconds cancel, and we end up with 3.96 times 10 to the minus 9 meters. All right, very good. All right, then the last thing here is that we just saw that electrons have this wave nature, and we saw earlier that waves have a particle nature, right? Einstein said they were quantized. E is equal to h nu, which is equal to hc over lambda, right? And this is, so this is the wave nature of particles, right? And this is the particle nature of waves. So we see this wave-particle duality. All right, very good. I think I'll stop there. And I hope you have a great Monday. And we'll be back live on Wednesday. So thank you very much for your attention. Have a great day.